I'm Jim. I've been here for about 3 years, CTO from the very beginning. Few faces that I've seen before. I was at Twitter for a couple of years, Square for a year, and then here for 3 years. This, just like Sean said, this is our first meetup that we hosted. This is the first time I've given this presentation. So hopefully it won't be too rocky, but there might be some rough edges to it, so bear with me. So the title of our presentation was, maintaining full data lineage over billions of data points. I think of this as basically how do we keep scaling data for our customers without scaling people, because we can't hire anybody like all the rest of you. I shouldn't say that in the room, but it's challenging to hire people right now. So we're trying to look at what can we automate more. We're standing on the shoulders of giants. We're not trying to compete with Spark. We're not competing with BigQuery. We're not competing with GCS. We're not competing with a lot of the core data path folks. What we're trying to do is just manage all of that stuff that actually has to go on behind the scenes over billions of partitions of data. Let's see if I can actually do this. Okay, so we're not doing. Sorry about this. So we're not doing a complete demo of our product. This really isn't about our product. Anybody with a blue badge would be happy to talk to you about what our product does. I do want to set a little bit of what we're trying to do and then tie that back in, because basically a lot of what we're talking about is stuff that we needed to do to make the product work. So what we give people the ability to do is develop pipelines. They can do it through the GUI, they can do it through an API. These pipelines that we're doing and projects are a bit different than what you would see if you look at something like airflow data flow graph. We're really not talking about jobs, but really just high-level sorts of operations. So we handle both SQL, we handle right now PySpark in a preview. But what we let users do is basically say, well, whatever data is on the input in this particular case, do this join against another table. They're not talking about where the files are. That's all sort of handled behind the scenes. They're not talking about how many files there are, all this partition information. It's a high-level representation. We do it on a fairly large scale. So we've got lots of graphs that are hundreds of nodes. This is where you need to manage all the stuff going on beyond the covers becomes critical. That's the entire extent of any kind of a demo. Like I said, we have full other presentations on that. I don't want to burden you guys with that. So now I just have to figure out another window. There. So the way we do this, and this is just kind of foreshadowing, we track data in our jobs. Jobs are difficult. We structure the data, and we represent that structuring of the data. We manage the persistence so that the user doesn't have to, and so that we can rely on it. And we're going to talk about transparent transformations, the ability to actually know what is going on and utilizing that. So what do a billion partitions look like? I'm not sure of everybody's background here. When we talk about a partition, there's the mathematical definition of taking a whole set of objects and then dividing them into non-overlapping sets. When we think about it from the big data point of view, we often mean a file that has a bunch of records in it. Many times in current data systems, we actually end up kind of fudging it and mean a directory or a prefix of a whole bunch of part files. So that's a partition of data. You often see people most commonly partitioning by date, because most of our big data is event data, which means it's coming in with timestamps on it. We do see, I can tell you, what we've seen with our customer base is a lot of ad hoc partitioning of data. We get data dumped to us on S3. It can have all sorts of stuff in there. A date component, but it can also have a device component. It can have source components for different websites. There's all sorts of stuff coming in. So where do a billion partitions come from? So we have one particular data source that we get 100,000 files every day, which is kind of a lot, and we didn't really expect it first. The reason you see this, again, and for folks that may not have seen this, is because a lot of times this is data coming in off of a queue. And that queue is sharded, so you'll have separate files because you need 3 copies of the queue in order to handle the bandwidth. And people want low latency, and the way that most of the storage systems, S3, GCS, HDFS, you can't read data until you actually close a file and create a new one. So you just generate this plethora. This is very common. You find it all over the place. So there's 100,000 files, and this is just for one single source for one particular customer, let alone there are hundreds of sources. That's 100 million jobs, 100 million files or objects a year. Which gets us up to 1 billion, depending on when you want to look at it. You either say, well, we have 10 years of data. This particular source, we don't have 10 years of data. We do have a deep pipeline. So if you take 100,000 files and you run a map on them where you're doing some row-by-row translation, you end up coming up with, if you don't do something else, 100,000 more files. So this sort of compounds quickly. And then for us, there's also, all of our rooms have our 4 principles on them. And one of ours is 10 by 100, which is whatever we're doing now, we're designing for 10x of volume. If somebody's asking us for 100 million files now, we're assuming it's going to be 1 billion next year. We also try to architect for 100x, what we're doing now. So all of this comes down to we need to handle 1 billion objects, which we're already handling across multiple, but even for a single source, we need that. Which, in most cases, that means 1 billion job scripts. We have to go read this data out of S3 and stick it someplace else. Certainly, we can combine multiple file reads, but there's still sort of 1 billion operations going on here, and we have to manage all of those. We can't. We pretty much just said this is insanity. We just can't do this. If you look at trying to manage Spark jobs, it's not easy and it's not fun. If you look at just taking this as just a random screenshot, not only are there a lot of them, looking at this list, you kind of have no idea really what they're doing. You don't know what they're reading, what code they're writing. So what ends up happening, which we've experienced, is somebody comes in, we get from somebody that's working with the data as a result and says it looks wrong. And so now we have to say, well, why does it look wrong? Maybe some of the input data arrived late. Maybe some of the input data arrived incomplete. Maybe some of it was corrupted. There's any number of different reasons. And this particular anomaly could have happened in a deep pipeline, could have happened anywhere along the line. It could have been source data that arrived late or incompletely. It could be between 2 stages for some reason. It actually, something fouled up. Big data, lots of things mess up. So the next thing is, well, how do we actually, okay, so we know there's something wrong. We've got to sort of investigate this. So what we end up doing is we got to go try to find the job that created this to try to figure out what went wrong within that job. So we've got lists of data, we've got to try to go through jobs and figure out when this data was produced, so give us an idea of what job actually did it. Then looking at that job, possibly looking at its logs, we started saying, okay, what files was this job reading? And what files did it write? So there's a lot of sort of investigation going on here. Our observation early on is identifying tracing jobs is really painful. I don't know of anybody that likes doing it. The link between data and jobs is pretty weak. If somebody that's a consumer of data says the data in this file looks wrong, getting from there back to the job is really a very not easy thing to do. There's a lot of investigation that goes on. And once we get there, once we've identified the job, trying to figure out exactly why it went wrong can be problematic because the world has moved on since then. Logs may be gone. The input that job read when it actually ran may no longer be the data that's actually out in the place where it would be needed now. And it's actually possible, if you're talking about somebody that says, well, actually this data from 2 weeks ago looks wrong, you're not exactly sure what the actual version of the job was when that ran. So the next thing is, okay, when we notice that the data has changed, what do we do? So generally this means we want to rerun a job, but what job do we want to rerun and when? Trying to figure that out again from the results that we have of logs and records of jobs is really not straightforward. An interesting part of this that comes up in our experience is, okay, so this data has been fouled up. What people immediately want to ask is, well, what data can I rely on? What data do we know that is not fouled up? Again, so we have to figure out what data got contaminated by this, by downstream jobs potentially, and what data is not. Our computations are heavily pipelined, so that means when something fouls up, if nothing causes the next step not to go, they all cascade and the data gets completely pushed through. All of this sort of recording of stuff we find really hard. So what we want to do is give up using jobs as a source feature. We're just going to say, look, jobs are too hard to sort of figure out what the heck is going wrong with them. Why don't we actually just understand what the status is of the data that we've written and be able to go from there. This is what we do right now by hand. Why don't we just do it as a first-class thing? So let's track the data, determine whether it's good, when it ran, what its relationship is to the input data, what actual transforms were actually computed, not the job. Which is easy to say, but the next question that begs is, well, why is handling 1 billion partitions if we have a partition per job? That's going to be easier than tackling 1 billion jobs. The thing is that unlike jobs, which have no sort of relationship to each other, all of our data, all of our partitions actually do have structures with them. None of us deal with 1 billion flat files in one particular directory, at least I hope not, without some sort of metadata that says these files relate in some way to the other files. We can leverage this structured hierarchy, and that's what we want to do. In fact, we do this all the time. Everybody that's out there building big data systems right now is actually leveraging this hierarchy to some extent. We have most of our systems breakpoint files out there so that they get concurrency. So when you say this goes into this particular path, what you really mean is it's not just foo, it's foo/part0, part1, part2. So we're doing that all the time. People use date prefixes all the time, or some sort of date string within it. Partitioning, there's even first-class partitioning in things like Hive and BigQuery that allow you to sort of start managing things. You don't have just one sort of undifferentiated list. Just as an example of something that you might see, it's very common to have a date prefix and a path, and then have a whole bunch of part files. Each of these is a partition of the data, put together, it's the entire set of data. There's a lot of metadata about partitions available. So if we look at a particular file out on S3 or GCS, I think we can do this in BigQuery too, we can get the E tag, we can get a hash of the data so that we know exactly what the data is. Well, we can detect whether there's a change to the data. We get modified time, we know when this data was actually written. When we write a job, we can certainly track this. We can actually say, oh, we read these 8 different files, here are the SHAs of those files, we wrote this file. So now we can say, when we go back and say, well, that file, the output of that previous run looks a little suspicious, we can actually see whether the SHAs of the inputs changed. So now we've got 1 billion E tags. You just kick this can down the road. So this is where things get really interesting. Why, if we can start arguing about, we do have prefixes. We do have these ideas of hierarchical partitions. We have this idea that all of the data within February of 2019 would be in a particular subfolder, and it's got all the folders under it. So we've been doing this same sort of aggregation of things to multiple levels of hierarchy for a long time. However, we're only sort of doing that, in that when you talk about a prefix, when we talk about the prefix of a file or talk about the path of a file, we can talk about what's a G tag. We can talk about when was it modified. When we talk about the prefix, meaning a whole bunch of files, we can't really say that. What's the E tag, if you, at least not as implemented by the backend system? If you ask for the E tag of a prefix to GCS or S3, it has no idea what you're talking about. If you ask for what is the modified time, there's no concept actually. Both S3 and GCS don't even have directories. So this is where we start saying, well, why do we structure our data and actually use first-class partitions? So we don't really, finding a way of actually describing this relative to big data is a little bit tough, but we've been doing this in other areas of computer science for a long time. We've got quad trees, and when you talk about the elements within a set, you can talk about all of the elements within this entire set as being all the elements in the whole block. You can also say, so you can talk about this as a partition, you can talk about this particular square as a partition. You can start talking about each of these things and talking about their content without just saying, these are not just containers of other partitions. They're a partition themselves, and they're first-class objects. When you ask for what is the number of records in a high-level container, like if you ask for the number of records in all of a data set for 2019, you can do that. You should be able to do that if this is a first-class partition without actually having to say, okay, I'm going to go sum up all of the, I have to go visit all of the children before I can ask that question. So this is semantically well-defined. It's very clear. If I have a directory with 20 files in it, all of us, I think, agree that the number of records in that directory is the sum of the records of each of the files. It's computable. It's not really complicated. It can be tricky to compute because it can be very expensive. If we have 1 billion files and we want to know what the number of records is, iterating through that 1 billion files and counting the records and summing them up every time we ask that question is really not going to work. So if you look at what we do today, we actually still have these concepts. Obviously, we have these paths which say, okay, here's all the 2019 data, here's the 2019 February data, here's the 2019 February 13th data. But we don't generally let the users just say, okay, run a daily summary for all of 2018, or figure out a daily summary for all of 2018. What users end up doing is saying, okay, what I want is this by day sort of aggregation. What I have to do is say, okay, the daily data is in these separate spots, and I will run a separate aggregation for each of those, which we tend to do with Airflow. So, or for example, we can do with Airflow. There's obviously other systems out there. That we take the original SQL, which has, group this by date, and we say, well, we don't need to group by date because we're going to actually run separate jobs for every day. So we tweak the SQL a little bit, and then we write a bunch of Python that sort of says, okay, here's where the files are, run this periodically. So the challenge with this is, one of the challenges with this is we now separated the semantics. Part of what we're doing is in the SQL statement. Part of what we're doing is in Python. Airflow, if you look as an orchestration system, doesn't actually know what any of the steps that it is doing. It has no representation for what these operations do. So it doesn't know what's being read and written. It's really basically just executing these things with their side effects. So there's not a whole lot that it can do to sort of say, well, these should be aggregated together. Spark, if the step in here is a Spark aggregation, Spark, when you run that individual Spark job for a particular day, has no idea that there are other Spark jobs that are going to be scheduled to run on other partitions of the data. What this means is there's not a whole lot that can actually be done to understand or to extract the metadata that we're talking about for hierarchies. There's no step in here that says, oh, once you've run all the data, all the aggregations for January of 2019, you want to actually aggregate that into a January 19 actual statistic itself. That leaves a burden on the user. The user has to decide where the data lies. They have to decide whether the data is up to date and keep track of it. Certainly something like Airflow helps a little bit. And they have to decide when the data needs to be used, when it can go away. All of this stuff, all of the interaction between the jobs that we're scheduling is all pretty much the responsibility of the user. They have to decide, I mean, a typical example of this is you have two steps within an Airflow graph that write data in the wrong place. The upstream data writes it in one place, the downstream job expects it in a different place, and nothing exactly works because neither system knows, the Airflow job doesn't know that the Spark job is expecting the data in a certain place, and the individual Spark jobs have no idea that Airflow is running two different things. So what that means is with a semantic split like this, and much of it imperative, since what we're doing in Airflow is imperative, the construction of the graphs is imperative Python, there's not a whole lot we can do to help in this particular case. This is a little bit of a dare for me. I've been trying to sort of figure out if this model is actually true and whether I can actually get people to believe it. But it feels to me like if you look at how we run jobs in Spark right now and compare it to what we do in assembly, it's not that much different. An assembler doesn't have, when you're writing assembly code, the individual instructions and the assembler itself has no idea what these things are doing. It is, you store data in a particular location and you read it in another location. The assembler doesn't do any data flow analysis on it. The processor, when you actually execute that code, just says, hey, I'll execute what you ask, but there's not much it can do about it. We don't write assembly anymore. We write higher level languages which is why we started building this higher level abstraction. I sort of said, okay, let's write this in a way where the user isn't writing every little, tiny little step. Let them express to us a broader sort of an abstraction, and we'll figure out how to do that. Show up. Wait, show up. So we start with a higher level abstraction. Now we can, from that abstraction, we can actually identify the data partitions that we need. From there, we can actually say, well, in order to have this partition, we need to actually synthesize a job to compute it. And once we've actually done that, we can actually aggregate data up partition trees because we're actually keeping track of them. So this goes back to our example that I showed a little bit earlier, plus the kind of trying to give you an idea of what our product addresses is. We let the user give us a very abstract sort of an idea. So if you have a set of data over multiple years that has some sort of financial transaction, what we want people to be able to say is, I want to know what the sum of the transactions are for each particular user, but by date. That's supposed to be day. I think that's approved by day. I want, as a user, to be able to write this and let the automation system figure out how many jobs that needs, whether they've actually run, whether there's data persisted out there, exactly whether I've got a day's worth of, whether I've got any data to run at all, whether I've got a day's worth of data, or whether I've got 4 years worth of data, so they know whether it's a single job or a million jobs. This definition, as we described it, is functional, declarative. It's not imperative like a job is. You don't actually say, run this. This is just a definition of the way the world should be. If data shows up on the left-hand side, the automation system should make the data, the appropriate transform data show up on the right. So the transformations are not jobs, they're just definition of mappings between partitions of data. This looks a little bit more like an Airflow DAG, not a DAG run. So it's a DAG in Airflow is run this, or this should be true for a set of dates. This should be true for a set of input values. We synthesize jobs. We don't actually decide to schedule jobs saying, okay, I need to run this job for this day, I need to run this job for that day. We actually say, well, this definition says I should have the data transform like this for all of this particular year. If it's not there, I better generate a job that actually produces it. If it is there, I don't need to run that job. The transformation behavior, as we see it, because we're trying to be declarative and functional, meaning no side effects, SQL statements are great for that. SQL is, by definition, a declarative language. Data flow graphs like Beam and Spark, the graphs themselves are this way. The actual languages for producing those graphs can be very imperative, but the actual graph that the systems actually execute are not. And this applies across the entire set of input data that's going into this. We're not actually saying run this for a particular file or run this for a particular date. We're saying whatever date range or whatever data range comes in, it should be produced on the result, as a result of the output. So this means partition organization. How do we organize partitions? We gave an example earlier. I gave an example earlier of date range, aggregated data. If we have a transform in there, we have the output data has to have some sort of organization to it. So what is that organization? If you're talking about a map in the straightforward map or use sort of model, the output organization should be exactly the same thing as the input organization. There's no aggregation going on. Every record coming in produces 0 to n records going out, but there's no intra-record sort of semantics going on. So if the transformation that we're doing is a simple map, that's what you get. If we look at the example of that we gave before of 100,000 inputs, this is a problem that's pretty commonly encountered within big data systems because of the same reasons. And you have people calling compact or compactions, which is, well, I have a whole bunch, I have 100,000 files coming in. Most of my downstream stuff doesn't want to deal with 100,000 small files. So you set up a transform that basically says, the output is going to be pretty much like the input, but I'm going to take some of the small white nodes that have very few records but have lots of files there and just combine them together to some level of, to the level of aggregation that the system decides makes its best guess at optimization. So you'll have a tree that looks very much like the original tree. A group by, especially a group by like we were talking about before, that does an aggregation by date, the output organization, if the input data is not organized by date, the output organization has got nothing to do with the input organization. It's strictly based on data, on the data structure, the structure of date. So I was going to show how this looks in our application, how this actually shows to the front end. This one, I think, that one. So this is an example of a little small test that we do as a demo. And so what we have on the left, and we're only going to look at these couple of nodes right here. One is we've got 4,000 files out on S3, arranged to the heck of. And so we reflect that. We read those in and we keep a tree. The tree that we'll keep in this particular case represents the tree, or initially it represents a tree as we see it out on the file system, on like S3 or GCS. Lots of interesting, one of our, I guess as a side note, as a company that sells to big enterprises where we're dealing with multiple groups, I can tell you, we don't have the luxury that I've had in the past of telling people that's a really stupid way to organize your data, because it's really hard for me to figure out how to list this data and aggregate it in very non-optimal, very non-obvious ways of doing things. So that's an area where we actually, Ascend has actually invested in coming up with algorithms for, we don't want people to have to actually, the users actually say, okay, I understand this, I'm going to figure out how to either change the organization, it's usually not allowed because it's different groups, or give a very specific way of actually listing the data. We can look at it and decide what the partition tree will look like. So this starts with 4,000. Here's our query, which is, in this particular case, aggregating by month. And so whereas we started with 4,000 files, the total number of partitions that this particular operation is actually going to compute, or in this particular case has computed, is 115. That means that over all of the input data, there are 115 individual months. One of the things about approaching it from a high level is the user in no way actually has to talk about the partition units whatsoever, other than indicating in the signal that they are actually aggregating this by month. Everything else can actually be extracted from this higher level description, which is why we feel like coming at it from a high level rather than trying to understand and optimize from a low level list of jobs is the right approach. We can show the data because we represent it. We actually track the metadata for every single partition that we either read or write. So in this particular case, we've written all of this stuff. And so we keep track of the date ranges of the records that we've actually represented. This particular visualization makes it look like our representation of this date information is flat. In other words, we're just representing it as a list of months. Internally, we have a hierarchy of this. It's just part of the current stage of the product, that when we show it to users, we only show it flat. So at this point, we have a bunch of flat partitions. When you still run jobs, have to be run on real data files. You can't run jobs on concepts or produce concepts out of them. So when we run, we actually produce, like in that last case, we create that list of group by date, group by month sorts of partitions. But we organize it into a hierarchy, and we actually propagate and aggregate that information over the hierarchy. So for example, if you ask what the modified time was for 2016, it'll take the maximum of the modifieds of all of the months within that particular, within the 2016 range. And we can do that because we understand how the data has been aggregated. this is kind of getting back to the very last part of this, which is what this does is it makes queries on a billion partitions order constant, which is really the key thing that we need to do in order to allow people to say, when was the output data created for this input data? We can actually look at the partition, we have metadata for it, and we know exactly what that is. This applies whether you're actually for a leaf, in other words, when did we actually produce the 2016 November data, but it also applies if you ask for 2016. In other words, when was the last piece of data? Because abstractly, the 2016 partition of this date tree represents all of the data underneath it. We don't do this because we understand hierarchy and because we persist the hierarchy and the metadata. We don't actually have to go through and enumerate all the little things to make this happen. We can ask in constant time, when was the output data created, what version of the transform. So this is where we get into the idea of tracking the provenance of things. Has the transform actually changed in this period? A big one is, do I need to, is the current output data as it sits on in wherever we've actually stored the result, does it actually reflect the inputs? Have we actually run all of this? And again, we don't want to go through a list of jobs and say, did all those jobs run? All we have to do is say, does the representations that we have of the input and the output, which we computed and stored when we ran them, consistent? Sorry about that, I can answer that any questions. An important part of this that we find very powerful is this works even if you're talking about something on the right side of the graph, talking about inputs on the left side of the graph. So because we're maintaining this data and data flowing it through all of these transformations, it's not just does this particular step, is this particular step consistent with its input? It actually, we can tell very quickly if new data has come in, which means this data that we have on the right-hand side, which will eventually be consistent, is not consistent right now. This works to the extent that transformations are semantically transparent. Do we know what they mean? If we don't know what this job does, what this particular application, Spark application, what a SQL statement does, we can't figure out how to partition it if we don't know how it's actually asked to be partitioned. SQL is transparent. SQL has very, very well-defined semantics. We don't have any problem understanding what it does. Data flow graphs, like you see in Spark and Beam, are transparent-ish. We can look at the graph. They're more complicated. We're not perfect at that by any means at this point. And there are cases where if you have things like user-defined functions, it's not clear we'll ever be able to figure out exactly what those things are doing. And if we don't know what they're doing, we don't know what transformations are appropriate. As soon as you get into arbitrary code, that's not. If somebody writes some arbitrary Spark job where we're not seeing, or I shouldn't say Spark, pick your favorite, read in something off of S3 and write it out on the S3. If we have no idea what that means, we can't really do much. We don't know what its results look like. If the transformations are transparent, which is part of the reason that we really pushed on SQL to start with, we can automatically partition the data, which was a big goal for us, both from our point of view of supporting our users so that we don't have to know what these billion data files are individually. It also gives the user a better experience because they don't have to understand how all this stuff works. We can optimize transformation graphs if we know what they do. This is stuff that people have done to some extent on smaller scales. Compilers do this all the time. We can optimize individual jobs internally because we can know, well, there's an example of this is, right now if I write a Spark job and say, okay, here's a set of data, write an output set of data, and one of the columns is an int, I really don't, there's not much I can do. I have no idea whether there's only one value for that int throughout the entire data set, or if it has the entire value, or it's a Gaussian distribution. Since we know what produced the upstream data, a lot of times we have a lot better idea and we can actually optimize the individual job. And we can do a lot of global static checks. It's kind of it's not exactly part of the billion data file. You could argue it is, but we don't have to actually run jobs to find out whether the schemas of the input and the output are consistent, because we data flow the schemas all the way through. If the transformations are opaque, there's not a lot we can do. If somebody says, I'm going to read this set of data files and I'm going to write this set of data files, we basically, if somebody says, here's a job, run it on all of your data for 10 years. If we don't know if that job is doing some sort of an aggregation per year, and therefore data from different years can't affect it, we have to assume that everything affects everything, which gets you into the world of total reductions. We do have manual annotation alternatives. If you give us a job, we can't figure out whether it's a map or a partial reduction or a full reduction, we can always let you tell us. Then it's just kind of this problem of if you get it wrong, we'll give you the wrong values. Getting to the end, if this reminds you of a compiler show, this is all very analogous to stuff that's been going on in compilers for 40, 50 years. If it reminds you of Spark, Beam, all of the data flow libraries that are out there, that's true. It looks a lot like those too. The difference is we're really focusing on intra-job versus intra-job. So it's the data that flows between two jobs rather than just within a single job. That means we're responsible for the persistence lifecycle of the data in between. Generally, your Spark jobs and your SQL queries aren't responsible for what they read or what they wrote outside of when they're reading and writing. Since we're doing data flowing through an entire graph, which includes persistence at many steps, we're responsible for the lifecycle of that. And we have to handle mutability. This is one I could do an entire other sort of talk about. If you think about a compiler and a Spark job, they're not worried about the program that they're compiling or the job, the program that they're running changing in the middle of the job. It's just not possible. If you go back to our application, people are going in there and changing those transforms all the time. So we've got to know, has this transform changed since the last time we ran it? Do we need to rerun it in order, when the user changes a SQL query, that we actually propagate the new values forward rather than the old values? And we can tell users, well, this job has changed. A node in this graph, 10 nodes up above you has changed, and therefore the data that you're looking at right now is actually not consistent with the data that we would produce when we get around to excuse me. That's it. Tracking data, not jobs. I found this to be, I don't want to say it's profound, but it's helped me sort of wrap my head around how we actually keep track of all of this stuff without having to do it manually. Structure partitioning, managing the persistence, and then transformation. Questions? Either now or later in terms of that made sense to me. I like this part. This is a little rough. We're working. We're a little startup. Come join us.
Hi. Questions? No questions. All right.
Questions? See the hand on the next person.